the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, and welcome to today's webinar in our AI for Earth and Sustainability Science Discovery Series. This is the second session in our series, and I'm Maria Pires from UV, University of Valencia, and I'll be moderating. This seminar series is organized by the ELIS program. ELIS is an European network of excellence in AI learning and intelligent systems. And in particular, it's organized by the Program on Machine Learning for Climate and Earth System Science. I'm organizing the series together with my colleague Gustavo Camps-Weiss from University of Valencia, and Marcus Reinstein and Jacqueline Densler from Max Planck Institute in Jena. And today we're joined by Claire Monteleone. Hello, Claire. Thank you very much for accepting our invitation. She's a professor at the Department of Computer Science, University of Colorado Boulder, and a research director at INRIA Paris. A little bit of her background is in Earth and planetary science in Harvard. She also completed a PhD in computer science at MIT and was a postdoc at UC San Diego. Also, she had positions in different universities such as Paris-Saclay, CNRS, George Washington University, and Columbia. Her research was pioneer in the use of machine learning for the study of climate change. And interestingly, she's part of the launch of this field of climate informatics. I'm particularly a fan of the International Conference of Climate Informatics, and you co-founded it. Congratulations, that's a very good initiative. And I've seen she also has participated in NeurIPS and ICML, so she's very active in the field. And I think today I would just give the floor to you to show your talk about confronting climate change with generative and self-supervised machine learning. So
thank you so much for the kind invitation and the kind introduction. I will assume people are seeing this in the full screen, not with the notes.
Correct.
Okay. Yes. So I'm going to talk about confronting climate change with generative and self-supervised learning, which falls under our work on climate informatics. I'm jointly appointed in Colorado and France, and here's a picture from Colorado where we had wildlife using a bridge, an infrastructure built by humans. And then we have nature, we have the creek and the forest, and then even a power line. And so somehow we're going to have to all live happily together. So this is sort of a happy image from Colorado. Here are several not very happy images from mostly from Colorado and California, but the same things happening here in the Mediterranean. And the increase of droughts, wildfires, floods, and the documented global warming has been a big driver in why I have been trying to use machine learning to shed light on and try to confront climate change for actually over 16 years now. And there's starting to be a big critical mass. The World Economic Forum at Davos put out a call to action in 2018 saying, look, of course, AI is driving industry and it's helping find cats in pictures, but can we use it to help protect our planet? And they cited climate informatics. And yeah, so I'll mention maybe a little bit at the end, but the next edition of the conference will be this coming spring 2025 in Brazil. So just to frame my larger scope of research, although today I'm going to talk specifically about methods and a few papers, we are working at a variety of different timescales. So those pictures with the landslides as a result of precipitation and drought, and those sort of extreme weather events that have outsized impacts on communities fall under climate change adaptation. How can we develop AI tools that will function in the very short term or near real time to provide better warning systems, and also to interface with society and take into account vulnerable communities that may have been made vulnerable by a legacy of climate injustice? How do we seek to rectify that? At the middle term level, what are some actions we can take now to reduce or attenuate the worst risks of climate change? And here we're mostly using deep learning techniques and using them to accelerate the renewable energy transition. And then finally, we can also work at very long term, the sort of time frame that the IPCC tries to predict or project using physical models. And we can use AI to combine the physical models and also sort of translate the physical models into more local impacts by learning sort of generative AI adapters where we do have historical data. But today I thought I would focus specifically on some techniques, give a brief primer on what is self-supervised learning and show how we can use it in this domain, what is generative learning, and show how we can use generative learning in this domain, and then end with some thoughts on climate data equity. Okay, so self-supervised learning is the common approach to unsupervised deep learning these days. And what do I mean by unsupervised deep learning? So we can abstract away, even in the supervised setting, all my choice of architecture, which comes with weights, parameters that I'm going to fit from my data, and just call a neural network with all those weights and parameters W. And so that defines a function F that when acts on an input, we'll just call the output Y hat. You may or may not know how these networks are trained. They're trained by trying to target an objective function. This is actually, we're usually trying to minimize a loss function. So when we talk about labeled data, what we mean is that for some given input X, be it an image, a vector, or a tensor of data, there is some target label Y associated with that in the supervised setting, be it classification or regression. And then the loss function is typically penalizing the network for how far its output is Y hat from the true Y. And what is learning? Well, you might have heard of back propagation. This makes use of the chain rule for computing gradients to basically take small gradient steps to try to reduce the loss and push back those updates into how I update my all my parameters in my network W. So backpropagation gets into how you update the parameters at different layers, but I'm throwing all those parameters just into W to make life simple here, and to distinguish the supervised setting from the unsupervised setting, and to realize that in some ways it's not so different. In the supervised setting, I do have this target label Y. Now, often in real domains, like when we address climate change, we don't necessarily have conveniently labeled data. We just have a lot of data, but we could still kind of use this framework. So there's no label Y. We can actually do something very similar. We can learn by doing gradient descent on a loss function and iteratively updating our weights throughout the architecture to walk in the direction of the decreasing gradient, as long as this loss function now, of course, doesn't depend on Y because we don't have it. And so what we want to do is define some kind of loss function that's really only a function of what we do have. So it can be a function of our data, and since we're trying to get our network to be better and better, we should also make it a function of the output of our network. So it's only a function really of the input data and the output data. Now we can do things to our input data to design this function, and I'll talk about how we might do that. First, as an aside, I'm not going to really talk about clustering, but clustering is an example where you have an objective function or a loss function defined on your data set, and it doesn't depend on any outside labels. So there's some early papers on deep clustering called ClusterNet. You can certainly set up an objective here that depends on subsets or mini batches or your whole training data for clustering. But say my downstream task is something like regression, classification, or interpolation of data in some way. Often the approach that is become very widespread is a self-supervised learning approach. If you have heard of contrastive learning, that also falls into this bin of self-supervision, where you want to come up with a pretext task. So new jargon, what do I mean? So I have my data set containing my X's. I don't have any labels Y, but could I set it up such that my loss function only depends on my input data and the output of the network, and still kind of set it up like a supervised learning task, even though I don't have labels. Then I'm going to train the model on that task. And this task is only any good as a pretext task if, after training, the features that I've learned will be useful for another task, meaning, I could rip off the final layer and use the features for some other task, or in some sense, I've achieved a representation of my data that's useful. This is pretty abstract. Let's go to a first example, and actually, this is a classic example, which is the idea of an autoencoder. So an autoencoder is actually the classic example of a pretext task. Why? Well, okay, I'm labeling these weights as encoder, decoder, but basically all of these things are my W that I'm going to fit. How am I going to fit it? Well, I'm going to computed only on my input and my output. Here, the training domain is grayscale images. But after learning, this is not a very interesting machine just to use. It's practically giving me the identity function, but even a little noisier. So I don't really need that. I don't actually need a machine that can push something through and maybe add a little noise to it. But this whole thing was a pretext for getting some kind of representation of the data distribution. So in this case, I used a lower dimensional layer, and so the weights that I obtain on that hidden layer are kind of bringing my data distribution into a lower dimensional representation. Okay. I will extend from here to the more interesting generative types of autoencoders, such as variational autoencoders, in the second part of the talk, where we are looking at both unsupervised learning and generative learning. But while we're here on self-supervised learning, which is an approach to unsupervised learning, let's give an example in the domain. So, whether you're doing adaptation or mitigation, addressing a task for a stakeholder, you often have data over space, so a latitude, longitude grid of data. And often you have some sort of time series of this data. There's satellite data taken at different times. There are products called reanalysis data that have been gridded over the globe using some physical balance laws. And there's actually purely simulated data, numerical weather prediction models use physics to make predictions. And then there's general circulation models, also known as global climate models, and regional climate models. Why do we have simulated data? Well, because we don't have any observation data in the future. And the amount that we have in the past is also very sparse because we haven't had satellites that long. Certainly not long enough to reason on climate timescales. Okay, so we've got latitude, longitude data. So at each latitude and longitude point, I have a real value. Say I'm looking at temperature, and then it's evolving over time. Well, this looks like, temperature over a latitude longitude patch could be an image. And now if we add time, we could maybe think of that as a video. And so we can go to our top computer vision conference and just take an off-the-shelf algorithm. That might work sometimes, but we have been focusing in on examples where that does not work and where we can design new algorithms to do a better job in these geospatial data domains. And one thing we sort of noticed is that there has been some underlying assumption that spatiotemporal data is video data, meaning Hollywood movies or something you capture with your cell phone. But that kind of data has some very special properties. There are depths, there are objects with edges, and even if you have a deformable object, it's a cat walking through, or even a school bus or a person, whereas our deformable objects are a tropical depression that might turn into a tropical storm, and then might eventually dissipate. So we have ephemeral patterns on fluids. And so this mismatch can cause a problem. A student of mine recently noticed that if you want to, say you have a time series of spatial data, geospatial data, and you want to interpolate it in time, so you want to have more frequent images than are available, then if we turn to the computer vision technique, and we want it to be unsupervised, the state-of-the-art self-supervised technique for temporal interpolation in computer vision at the time was called super slow-mo, and it relies on optical flow. But most of the state-of-the-art techniques for this do rely on this same idea of optical flow, which produces these horrible artifacts. So what is optical flow doing? It's looking at groups of pixels that have similar behavior and have sort of similar trajectories as you move along the time dimension, frame to frame. This works really well when you have, a 60 frame per second video, and when you have edges and actual objects that can be detected. On this smoother fluid dynamics taken at lower time resolutions, it leaves these awful artifacts that you can see. And these are two very different data sets. This is completely simulated data at the bottom from a global climate model that contributes to the IPCC. And on the top, we have a fine resolution reanalysis product. So its source was originally observations. So as a punchline, the pretext task that he came up with enabled this algorithm called stint, which does not have artifacts in either of those two types of geospatial domains, and looks a lot more physical, and you can compare it against the ground truth. But, you know, it was not trained on the ground truth. It was trained in a self-supervised way. Okay. So how do we do that? So he actually came up with a pretext task for the problem. We had given autoencoder as a general example of a pretext task, but in this case, we're trying to interpolate a spatial image in time. So the input data I'm indicating in this bluish color. So we have the image at time indexed by these integers 0 through 2. And so we're going to train a model F. So F has a subscript W with all sorts of parameters. There's choice of architecture, etc. But what does F need to be able to do? Well, if it's given the images on the two endpoints, time 0 and time 1, it should generate or output an image at the midpoint. And so these are what the model F would generate on being applied to time 0 and time 1 and time 1 and time 2. But you can notice that then the same such architecture should be able to interpolate an image between time 0.5 and 1.5, and that generated image should be comparable to the real image at time equals 1. So the loss function is going to be checking for cycle consistency. That so we just have, you know, one set of weights F that we're learning. This is the same F here and here and here, but we're training. We're update. Wait, why is my slide not advancing? Okay, we're updating our weights to minimize this loss function of how far this generated image from F at time t equals 1 is from the real input image that we had at time t equals 1. It's a very simple, beautiful idea. And actually, we have two such checks because we can also check, the image, both of these images. Sorry, actually, here's just one check. We're comparing to the image at t equals 1. That's the idea. I wanted to start at the very simple level. He actually showed that to deal with regularization and avoid overfitting and avoid trivial solutions, he actually needed to have several levels and several cycle consistency checks, where some of the cycle consistency checks are at two generated images from the architecture, like the purple ones. And then these yellow are back comparing to one of the original input images. So the loss function is trying to pull the generated image close to the real image in the particular time frames. And so he had a loss term for each of these cycle consistency checks with knobs. And then he tuned those knobs, and as expected, it turned out we wanted to have more weight on the checks that compare to real data than the internal checks, but the internal checks did help with regularization. And so across a range of different kinds of data, so not only simulated GCM data and fine-grained and coarser-grained types of reanalysis products, but also over some satellite imagery data sets, that we had improved performance on this task versus super slow-mo. And comparing on a standard video benchmark, we did not outperform. If we did, it would be a computer vision paper, right? And so we're contributing more to the climate change literature here. Okay, and I also promised to talk about generative deep learning. And so recall the autoencoder, it's taking a loss that is trying to pull the output close to the input, and by minimizing this loss, you update your weights to get some compact representation. If you're sending it through a dense layer, meaning something lower dimensional than your actual data space. Sometimes people send it through a wide layer if they're interested, for example, in cognition. There's evidence that in cognition in some insects and possibly in humans, we go to a higher dimensional space to record our perceptions in order to well separate them and class it and distance them from each other. But mostly in many of the applied domains that you might encounter in addressing climate change, you're probably going to do this to get a latent representation and reduce the dimension. And so before you add any probability, you're just training on many input images and trying to get an output similar to the input. So at the end, you'll get the weights at the dense layer as a compact representation of the whole data distribution that you trained on. But given that you trained on a data distribution, wouldn't it be nice to have a distribution over latent representations, which we call a distribution over a latent space? And the first idea for that was the variational autoencoder, which fits a Gaussian. So you start with the parameters of a very simple prior belief, maybe a spherical Gaussian, and then you slowly adapt your parameters because you're learning them inside the network. Then if you want to get away from a Gaussian, normalizing flows came out, I guess, about 10 years ago now, which you start from a simple prior. Here's an isotropic Gaussian, and then you add désolé, sorry, pas maintenant, merci. Excusez-moi, sorry. You add complications by composing bijections, these little Fs, and you learn the parameter of these bijections. So you get a flow that complicates your prior to better match your data. Now, of course, you don't want to overfit. So you'll have a regularizer that's trying to pull your distribution close to your prior as one of the terms that you're trying to optimize. So they're cleaner in some ways than VAEs because they learn a proper distribution and they generalize it to other kinds of distributions. So I'll give an example of how this can be applied to study climate change. Many of the things that we're asked to do for adaptation or mitigation involve downscaling data from a coarse spatial grid to a fine spatial grid. If I look at the models that are informing the IPCC, they're looking at larger grid boxes in order to predict farther in the future than what communities and stakeholders are asking for when they're asking, where should I put the next wind farm? And so just the idea of going from a coarse resolution to a fine resolution in the geoscientific domain is called downscaling. In computer vision, it's called super resolution often. And so we did, this was led by Brian Gronke, who did his master's with me, a study, two separate studies, one for temperature and one for precipitation. And the data sources were different. We had real data from an ERA 5 reanalysis data set, and that's what we had at a coarser resolution, and simulated data from numerical weather prediction data set, and that was at fine resolution. But of course, for the AI method, it doesn't really matter too much what the data sets, how they were generated, But you'll see they're over the same large bounding box, which was looking at part of the continental US. So we took a generative AI method and applied it to downscaling. And the domain alignment task is I've got two random variables, and I want to be able to approximate the marginal distribution of one given samples from the other. And then I want my F to be invertible, so I can also approximate the marginal of the other variable given samples from the first variable. I'm using X and Y, but I'm not meaning that Y is a label. I'm just saying we have two random variables. So in our application, the two random variables are the data field, say temperature, at low resolution, and the other variable is at high resolution. And interestingly, we do not need paired maps. So if we look at the domain, the work in the domain, most statistical climatology, statistical downscaling techniques would need a paired map. So if I have a map of precipitation and coarse resolution on a particular day, I need the map in fine resolution in order to train my downscaling method. Here, we just need access to maps at both resolutions, but they don't need to be aligned in time. The method does better if they are aligned in space. So the idea of this domain alignment paper, Align Flow, that came out a few years back in AAAI by Grover and others, is that, okay, ideally we would like the joint probability distribution over X and Y, my coarse and fine scaled variables, that would allow me to generate samples. It would allow me to generate samples conditioned, so I could look at a fine resolution and generate a coarse resolution, or vice versa. But we can drastically simplify our joint by making a conditional independence assumption that X and Y are conditionally independent given some variable Z, which we will have as our latent space. So we assume some prior there, and then we just learn normalizing flows. One giving an invertible map between the low resolution data space and the latent space, and similarly for the high resolution. So this was the architecture. It was largely following Align Flow, but Brian used the GLOW normalizing flow as the instantiation of the normalizing flow. And where do we learn parameters? So we have a sort of actor-critic loss function for both of these flows. We have regularization terms, making sure things don't get too far from their priors. But we're learning network parameters just for these flows, by having a joint loss. And there's a lot of other things you don't have to worry about. Implementation detail is that we have one sized representation for our distribution over the latent space that starts as a prior and ends up as the learned posterior. And so we'll set that to be the same shape as the high resolution images, which means we have to just, in the most non-adding information way, just upsample our low resolution data. Once the model is trained, you can use it in a variety of ways. And so this is unsupervised or self-supervised with respect to space. With respect to time, and it works better the better the spatial alignment is. It's generative, so I've now got this probability distribution I've learned over Z. I can sample from it and push it through the flow towards the fine resolution map to generate as many fine resolution maps as I want. That's called unconditional sampling, or similarly for coarse. Or I can do conditional sampling, meaning I condition on maybe a fine resolution map and then output coarse resolution maps by going through the flow to a point in the latent space and then sampling from there. Then you can do some interpretability studies. You can say, look, after the model is trained, if I give it the top images at the left and right, which were precipitation maps at different times, can I make an interpolation between them? And the way the model does that is it maps down to the latent space. I'm not visualizing the latent space, but I can then sample from that to get coarse resolution maps, and or I can interpolate between points in the latent space. How to do that is now a very interesting field in core machine learning, how to interpolate between points in the latent space when you have this non-trivial posterior, you're trying to walk a geodesic on it and you want to do it so efficiently. And then from each point in the latent space to generate images. I see that I got a question. I will, okay, maybe can I get to that towards the end?
Yeah, Claire, we will answer the questions at the end.
At the end, okay. But yeah, thank you for populating the chat with questions. I really appreciate that. So the summary from these papers that I showed is that we can design a pretext task and do self-supervised learning to downscale data in time or temporally interpolate geospatial data. And this works best when the input data is spatially aligned. And then we can do an unsupervised and generative technique where we get a probability distribution out of it to downscale geospatial data in space. And it's also unsupervised in time. We don't need the temporal alignment of the coarse and fine scale data, but the better the bounding boxes that align them, I mean, the bounding boxes of the coarse and fine resolution data line up, the better this thing works. So one outlook or future question that we are interested in is, can you simultaneously downscale in space and time? Is this a good pretext task that's useful for other downstream tasks? If not, what is a good pretext task in the space and time domain simultaneously that is useful for other downstream tasks that we care about with geospatial data in addressing climate change? And we're continuing to push on generative learning. One of my PhD students just published on probabilistic temperature predictions, where you can basically generate an ensemble of forecasts probabilistically, given a forecast generated using the traditional physics by using deep learning. And we're applying some of the ideas involved in generative downscaling to do longer term planning of where to put solar panels and wind turbines to make them more future proof, since the winds and the clouds are changing. We're also using diffusion training protocols to allow us to generate, which is another form of generative deep learning that I didn't have time to talk about, to be able to emulate a global climate model or certain fields of it, and generate a whole probabilistic ensemble of realizations to try to reduce uncertainty on predictions at longer timescales. I did want to leave some time to seed the discussion around climate data equity, which, I'm really glad to see, especially from the intro film, that AI for Good is really interested in, issues of using AI for social good. And I will give a trigger warning about this unfortunate graphic. This was put together by meteorologist Jack Sillen in the US, and it came out in a paper by McGovern et al. And he overlaid population densities of Black Americans, African Americans, in the grayscale with weather radar indicated by the circles in green and yellow. Now, we don't actually have weather radar everywhere. It's an expensive sensor, and we don't have it everywhere, but it's not uniformly distributed. And if I just read from the legend, he says, many majority Black parts of the Southeast USA are relatively far from weather radar sites, meaning that it's harder to gather information about storms impacting these areas. So this is terrible. And it means that before we even think about what architectures to use and think about fairness there, we're up against real inequity in what data is even being collected and is therefore available. So AI is not going to be the solution here. Clearly in the US, we need political intervention so that this kind of thing is fixed and never happens again. But I do think that those of us using AI in this domain can make it a force to improve climate data equity. And this, in part, just traditional supervised machine learning could work, meaning if you have a remotely sensed product that covers the whole region and you only have radar in certain regions, then you can learn models that create sort of synthetic radar measurements where you don't have it by doing supervised learning between the remotely sensed data and the locally sensed radar. More generally, though, we like leaning on unsupervised learning, so we can really get as much information as we can out of the data that we have. If we have extremely low data regions, then we want to get as much information as we can out of there. We can also train unsupervised methods in the high data regions and then either apply them directly in the low data regions or fine tune them if we have some labeled data we can fine tune with. So basically, can AI help push the benefit from our high data regions to our low data regions? If you're in the US, you're probably aware of the environmental injustice legacy that we have there. But more generally too, I mean, the industrialized global North has contributed more to climate change because its industries have emitted this anthropogenic carbon that has caused the warming. Yet at the same time, North America, Europe, and other industrialized countries typically have a denser network of weather stations and just more data. And meanwhile, the developing global South is often suffering at the moment already from the warming resulting from climate change. So just as we can go from the high data region of the current observation period region in time to project about the future, I would like to, spread the benefit of the high data regions to the low data regions spatially using AI. That is pretty much it in terms of the research. I'd like to thank my research groups, both in Boulder and in France. Climate informatics was alluded to. The next conference, as I mentioned, is going to be in Brazil. Watch climateinformatics.org for the exact date and location in Brazil. We're really excited, though, to finally go to the Global South after holding it in North America and Europe and online during the pandemic. There's a journal. So if you're working in this domain, if you're attending this webinar, probably your work is related. If you're using any kind of data science or AI on environmental questions, not limited to climate change, please submit. There's also an open call for working groups at this Environmental Data Science Innovation and Inclusion Lab that I am a part of. And that's very interesting. So if you are an ecologist, they're especially favoring applications in biology, or if you work somehow at the intersection of sustainability or biology and data science, then you can get these fully funded trips to Boulder, Colorado, to be part of a working group in a team science, in a data synthesis center. And we're going to have postdoc positions and annual summits and unconferences and hackathons. So with that, I will turn it over for the discussions.
Thank you very much, Claire, for this fantastic presentation and introduction to, you were able to cover like two very state-of-the-art approaches, climate with very clear examples, and I particularly enjoyed the data equity part. So thank you very much for preparing the seminar and sharing with us your research. I think we got one question in the chat, so I can read it out. And it's from Moyen Rangsan, and the question is can you explain further why video models doesn't work well on geospatial data? Could it be because of low spatial resolution of climate data, or is it true for high resolution remote sensing data as well?
Thank you. Let's see. Thank you for the question. Let me just go back to where that was.
Yeah.
That's a very good question. Now, we actually do have results. Okay, so these are results at two differing spatial resolutions and differing temporal resolutions and differing data types. So on the top, CARA is a special reanalysis product over Greenland, which means it was based on different kinds of measurements, including remote sensing products, which was then passed through, physics balance equations to get a gridded product. Whereas this IPSL is a global climate modeling product that's at a much coarser scale and is completely simulated from physics other than initial conditions. And then in his final results, he also has results from Sentinel. So this appears to be the case across all those different data types, and it does not seem to be due to the spatial resolution of climate model data. There's one technical issue, which is that there is some chance that if you had really, really high frame rate geospatial data, perhaps the optical flow assumptions could maybe hold, but we don't have depth or edges or objects. So these objects are being spuriously tracked, leading to these terrible artifacts. The other thing is that as you go to finer and finer spatial or temporal resolutions, there's usually still signal in geospatial data. So you might have, in time, you have overlays of the daily cycle, the seasonal cycle, and even longer modes of variability like the El Nino Southern Oscillation, also superimposed on top of each other. So there's signals at low frequencies, high frequencies, and as you downscale in time, you're going to potentially still have information. Whereas if you zoom in, farther and farther on a cat, you basically get a uniform texture that it's kind of easy to generalize from. You don't have kind of this fractal nature that you have with what's going on fluids. Okay, there's a few more questions now.
Yeah, but before jumping to the second question, follow up on that, and my experience also with self-supervised if using remote sensing, if if you use computer vision approaches and you just apply it to remote sensing data, they're not optimal in a way that they use a lot of resources. And by accommodating the approach to the particularities of the models, of the data, sorry, like we have spectral information, and then we have that temporal, as you said, teleconnections and things like this. It helped make the models less computational intensive. So in the end, they were more sustainable in a way. So do you have that feeling too with the climate data?
So a quick comment about sustainability. In other works, we're doing things like emulating climate models or doing AI-driven weather models. And that's a case where actually AI can have a big win, because once trained, they're much, much quicker to predict, to make predictions than the existing techniques. And so it's one small place where AI can actually reduce compute. And if your compute is powered by electricity that is not carbon neutral, it can help you reduce, the carbon impact. Another area, actually, relating, and this is not a work I mentioned, but we have a manuscript with another student in process where instead of forcing the data to be into a data cube, he's using all the different types of data that you want to fuse at their native measurement dimension and redesigning the architecture so you don't have to bring everything up to the same resolution. You can actually get a lot of computational savings there. So we do try to keep it in mind. I wouldn't say that necessarily all methods using AI are more efficient than those without. I think that's wrong.
No, I was just saying that if you accommodate the machine learning to your input data, not just take it from computer vision, but with remote sensing, you accommodate it to the remote sensing particularities, or with climate data to, the input data you have.
So in this case, we did take the super slow-mo algorithm and retrain it for each of our geospatial data sets. We didn't use a pre-trained video model. But I would have to go back and look at how that affected compute. Thanks for bringing that up. The other thing is that if you're able and willing to learn a model from scratch, how to train it, then you can do that. But it's also interesting if there are foundation models out there that can then be fine-tuned to the different tasks. And that's an effort that a lot of labs are taking, including in industry.
Definitely. Yeah, thank you. So we can jump to the second question. And it is about the last map that you showed, about the map for the entire population of the US. And the question is this map available for the entire population or the white American spatial distribution too? It is just to ensure that the effect zone is not only due to people moving out of regions that show significant weather phenomena.
That's a great question, and I don't have the answer. So I don't know how to track down Jack Sillen, the meteorologist, but you could maybe contact the authors of this paper in the EDS journal.
Yeah, I think that's a very specific question about the data, but this was a great example. Yep. Well, in this, related to this one, I think that was a really good idea if you have for instance, the in situ radar, and perhaps you want to use synthetic data to generate in other regions, but you could also leverage from satellite data, perhaps. That was my question. So you have satellite data, it covers the whole world, but in situ you only have in few places. So perhaps you can leverage for
So that
two.
is what I tried to say. Maybe it was unclear because I just called it a remotely sensed data product, but yeah, a satellite product. You would do supervised learning, where the label is the radar and the input is the satellite data. And then once you've learned that model, yes, you would go ahead and apply that to areas where you have satellite data and you want to generate synthetic radar data. Exactly. And I think, so this is like a field called virtual sensors. I think that NOAA is either they're already doing it or they're very interested in doing that exactly for weather radar, as you mentioned.
Okay, yeah, I've seen several works in that direction, but this is really something I think as a community we need to push, since the models are better when you have data. So if you can bring it's very expensive to put in situ data everywhere, but we have satellite data everywhere. So if we can bridge that gap, so I totally agree. Okay, we have one more question, and it is from Jacob Willem Bruin. He thanks from the interesting presentation. And then he asks about a presentation you hosted about ForecastNet. This is where Fourier transforms of weather and climate data are used to train ensembles to great effect. Okay, have you used similar techniques using transforms of data or handmade features instead of the data itself?
So first, that's an algorithm out of Anand Kumar's lab at Caltech, and also she used to be leading a team at NVIDIA on that, and so that that model ForecastNet came out of NVIDIA. And I first want to mention that whether you use Fourier neural operators or whether you use graph neural networks, sparse graph neural networks, diffusion training, what have you, a bunch of different high-tech companies have been jumping into this AI for weather revolution, which has been really exciting. So NVIDIA is one. I think some of the top performers right now are GenCast out of Google DeepMind and several models coming out of Huawei, but Microsoft has a model. A lot of people have jumped in. And I want to first mention the importance of data, especially on this slide when we have the data. What enabled all of those deep learning models to do a good job at learning an autoregressor to do a day ahead full weather state and be able to roll it out 10 days and have better skill than the physics-driven models is a training data set called ERA5. And just like ChatGPT is only smart because it's trained on things that smart humans have written, these models succeeded largely due to the quality of this ERA5 data set. And that was generated with European Union dollars, part of the Copernicus project, and many, many human hours in designing data assimilation algorithms to take observation data and grid it using physical assumptions. So yes, and there we're seeing skill from a wide variety of methods. I don't think ForecastNet is sort of ahead of the pack at the moment. And then we're seeing other hybrid techniques that are trying to do much longer term climate modeling. And we're also seeing people bringing in observations more. That's also what we're interested in now in our team. But have we used transforms and handmade features? I did have a master's student looking at that for a while, and it's a really interesting trade-off, right? Because you can drastically reduce training time, and I do think that's a pretty promising direction. Neural operators in particular are very exciting because you can sort of like just train in your discrete set of data, which is just a discrete view of the world, and then sort of continuously interpolate between them. And it's behind a lot of advances such as diffusion model training.
Okay, thank you. Perhaps I can just ask one last question, and if there's no more questions on on the chat. And this is about, you saw the examples of temporal interpolation and spatial downscaling, and you learned that from data. Have you tried it for prediction? Or perhaps I didn't understand, but have you tried to prediction to the future? So if for instance, in climate change scenario, no, like I'm thinking of prediction of streams or something like this, where we don't have a lot of streams, or we will have more streams. Can you talk about this, or perhaps using more inputs, not only LST, land surface temperature, but having a lot of data, so you learn a representation you can forecast?
So what was the application? Streams, like rivers? Is that what you're saying?
No, climate streams. I was thinking about heat waves or droughts or
extremes.
Yeah.
So this particular one is doing temporal interpolation, and then you're saying after the model is trained, can you do it for forecasting? We haven't tried that, but we do have actually a whole. I didn't talk about this because we're not using generative or self-supervised AI there yet, but we do have projects on extreme weather. So for example, I started with those pictures of floods and droughts and wildfires. And yes, we want to get better at predicting, at forecasting those. And if you think about the revolution in AI for weather, whatever deep model it was, whether it was your FNO model, as was mentioned in the comment, or a sparse graph neural network, the choice of loss function to get good performance is often optimizing for good average performance, like minimize your root mean squared error of your prediction with respect to the ground truth. So that makes us question how performant these would be in the tails of any particular distribution, which is where the extreme events would lie. And so I have one student doing his thesis completely on that. So how can we make AI weather forecasting systems better at dealing with extreme weather? Now, the first thing is that when you have that much compute and that much data as a Google DeepMind or a Huawei, you actually already can do very well, even just training on an RMSE. They actually predict like hurricane tracks 10 days in advance with skill better than the standard ECMWF forecast based on physics. So there might not be a huge room for improvement, or maybe there's some extremes that we can help with. We have found that incorporating new observation data in can really help, and that if we look at a reanalysis product like ERA5, after all that smoothing to get a gridded product using physics, the extremes often are lost. So if you compare to a remote sense product and that from which you can derive like wind intensities, the observed wind intensity maxima in the actual observation product are not matched in the ERA5 training data. My student checked that. And so then we, kind of want to fuse data from a lot of different kinds of sensors. If we're thinking about satellites, we might have multiple bands, but when they're measured on different satellites, the sensors themselves have different behavior, they're not aligned. So there are a lot of really interesting questions around data fusion before we even get to how do we want to redesign our loss function to prioritize extremes. But yeah, that's an interesting line of work. I hadn't thought of the temporal interpolation for that. We actually are, there's just like a technical step that we have to get to when you use satellite data. You might have a 6-day time step between measurements at the same position. Could we do temporal interpolation first to get a richer time series? And then that might help with the extremes.
Yep, thank you. Okay, so yeah, I'd like to thank the audience for the questions, and I'd also like to thank Claire, and I think we have some space now in the neural network for chat afterwards. Yeah, I'd like to close the session. Thank you very much.
Thank you, Maria.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Mm-hmm.